So sample problem 21.4 is kind of a detailed problem. It's going to take us a little while to write all the things that we need to write for it, but conceptually it's a pretty straightforward problem. I'm going to talk through part 1, and I'm actually going to solve part 2 first, and then we'll go back and we'll do kind of the nitty-gritty of working through the details of part 1. Part 1 says, combine the following 3 half reactions into 3 balanced equations for spontaneous reactions, calculating E cell for each. So again, having 3 reactions, A, B, and C, we have to combine them in different pairs. So we're going to have an A and a B combination, then we'll pair A with C, and then we'll pair B with C. And again, we'll always have to flip one reaction to make it an oxidation reactions, because all of these are written as reduction reactions. So we've got all of our electrons on the left. So we'll flip one of them, combine them together, and then we'll figure out E cell. That's just going to take a little bit of writing to do. So I'm going to work that out second, because from a conceptual standpoint, I want to think about this second part. Rank the relative strengths of oxidizing and reducing agents. So before we kind of answer the problem, let's make sure we understand what an oxidizing agent is and a reducing agent is. So an oxidizing agent is a species that has been reduced. And this terminology is important to understand because you'll see it used kind of interchangeably. So if we want to talk about oxidizing agents, that's somebody who's been reduced. Well, the only way that somebody can be reduced is if somebody gives them electrons. So something that's been reduced is an oxidizing agent because it's an agent that forces someone else to lose their electrons or be oxidized. I know that's kind of a mouthful to think about, but again, something that's reduced is an oxidizing agent. So the strongest oxidizing agent is the species that most wants to be reduced. So if we look at the species that we have here, right? So for reaction A, B, and C, let's identify the species that's being reduced. We've got NO3 minus being reduced in the first one. We've got N2 being reduced in the second one. And then we've got MnO2 being reduced in the third. What we can do is we can look at these standard reduction potentials. Remember, if we want to make a spontaneous reaction, we need to combine this with an oxidation standard reduction potential and have an overall E value that's positive. So the more positive this value is to begin with, the more that guy really wants to gain electrons. So what we can see here is if we just rank these, we can see that this is the largest number, which means that this guy wants the most to be reduced. He has the greatest affinity for electrons. The greatest standard reduction potential is the greatest affinity for electrons, so he wants the most to be reduced. We've got the greatest affinity for electrons, and whoever wants to be the reduced the most, has the greatest affinity for electrons, is going to be the strongest oxidizing agent. So MnO2 wants the most to be reduced. Then we're going to have NO3. So again, if we write this in terms of oxidizing agent strength, so this is oxidizing agent strength. MnO2 wants to be reduced much more than NO3, and then much more, we can even put 2 arrows there, much more than N2. And hopefully this one makes sense, right? We've talked about nitrogen gas a lot. Nitrogen gas is fairly inert, fairly unreactive, so it's not surprising that it doesn't want to undergo any reductive chemistry and generate a reduced species. So again, this is the trend that we'll see for oxidizing agent strength. So a little bit more quickly going through, again, a reducing agent. So if we consider somebody who's a reducing agent, this is a species that has been oxidized. So what we need to do here for reactions A, B, and C is we actually need to look at the flip of these reactions because we need to think about these being oxidation reactions. So if we think about them being oxidation reactions, we've got NO being oxidized in the first one. We've got N2H5 plus being oxidized in the next one, and then Mn2 plus. So what I'm going to do here is I'm going to write these as oxidation potentials. And again, we want to find the largest positive value. So in this case, we're going to have negative 0.96, going to have positive 0.23, and we're going to have negative 1.23. So this guy most wants to be reduced. Most wants to be oxidized. So he is the strongest reducing agent. So again, if we draw a little trend here, we've got reducing agent strength. We're going to have N2H5 is going to be much greater, and we can even say it's much greater than NO, which is greater than Mn2+. So kind of some qualitative things here that we can take from quantitative reduction potentials or oxidation potentials. So what we're going to move on to now is actually solve part 1, which is look at these different combinations, the A and B combination, the B and C combination, and then the A and C combination. Okay, so we'll run through all 3 of these. So I've taken the liberty of making the AB, AC, and BC combos a little bit easier for myself, that I've actually just copied and pasted the reactions here. So for each of these, in order to end up with a spontaneous electrochemical reaction, we have to figure out which one of the 2 reactions we'd flip so that when we sum them, we still have a positive E cell. And so, for example, with this guy, we can see that this is the one that we'd want to flip so that we'd have a positive E cell. For this one, this is the one that we'd want to flip, because making a negative 0.96 summed with a positive 1.23 will still give us a positive E cell. And again, with this one, this will be the one that we want to flip. So part of kind of combining things together to have a spontaneous reaction and a positive E cell is figuring out which reaction will become your oxidation reaction, which is the reaction that you'll flip. But then you'll also have to think about how we scale these reactions with coefficients so that our electrons gained will equal our electrons lost. So I'm going to kind of go through and kind of write how we scale each one of these, and rather than rewriting it and then writing it again to sum it, I'm just going to rewrite the one that we flip, and I'll scale that one at the same time, and then we'll just kind of mentally make sure that we use the right coefficients in front of this. All right, so this guy we're going to flip, and hopefully everybody realizes the common factor that we need to scale these by. Multiply that guy by 4, multiply this guy by 3. So flipping this one, we're going to have 3 N2H5 plus. And again, I'm going to keep my phases out just to keep my writing simple until I get to my sum at the end. So again, we're flipping this guy, so then we're going to have 3 N2 plus 15 H plus 12 electrons, and this is now going to be my oxidation process, so it's positive 0.23 volts. This one's going to be my reduction, and again, I'm going to go through, and just so that I don't miss pushing my 4 through, this is going to be a 4 here, this is going to be a 16, that will be 12, this will be 4, this will be 8. Again, a lot that we've written here to kind of sum all these up. So this guy we've already flipped, so that's not going to be the one we're using. We're summing it with this one. So let's go ahead and sum these. Anything that was on the left we'll keep on the left. Anything that was on the right we'll keep on the right. And we're going to put our phases back in. So 4NO3 aqueous plus 16H plus aqueous. Again, our electrons are going to cancel, so I'm not going to write our electrons. But then we've got 3N2H5 plus aqueous, so that takes care of the 3 species that were reactants now. In terms of products, we're going to have 4 NO gas plus 8 waters, and then we've got 3 N2 gas, right, and then 15 H plus aqueous. Now, particularly with these monster equations, sometimes what we have to do is find things that are common on both sides and make sure that we reduce them. So we got 15 protons over here, 16 over here, so that will leave us with 1 over there. And that's the only thing that's common on both sides. Sometimes you'll see that water might be common on both sides. But again, now to do E cell equals reduction standard potential plus oxidation standard potential. So that's positive 0.96 volts plus positive 0.23 volts. So we have an overall positive 1.19 volts. And again, we wanted to make sure that this is spontaneous, so it should have a positive E cell. All right, let's go through this for our next one. Again, having to flip and looking at these here, we're going to realize that we need to scale this one by 3 and this guy by 2. Because I have to flip this one, I'm going to flip it and put my coefficients in. So 2NO plus 4H2O. I'm keeping my phases out to just keep things simple. 2NO3 minus 8H plus 6 electrons. Again, I'm making this my oxidation. So negative 0.96. This is my reduction. I'm going to go ahead and push my coefficient through here so I make sure that I don't lose things. I'm going to go ahead and sum these up. Right, this guy I'm not using. These are my 2 that I'm summing. So we're going to have 3 MnO2 solids plus 12 H plus aqueous. Electrons will cancel, plus 2 NO gas, plus 4 H2O liquids. And that's all my things, 4 things as reactants. Products, I'm going to have 3 Mn2 plus, 6 waters, 2 nitrate, 8 protons. Now again with this guy, we're going to find things that might be common on both sides. We can see here that we're going to have waters that are common on both sides, 4 of them and 6 of them. So I'll have 2 left over here, 12 protons and 8 protons. So I will have 4 of them left over here. All right, our last one. Same thing here, except for this one I can see that I only need to scale this guy by 2, and I need to flip this guy. So I'm going to go ahead and flip him just so I can have my right species. So this now again is my oxidation, positive 0.23. Go ahead and I'm going to push this through here so I have my right coefficients. Sum these up. This is my reduction. So 2 MnO2 solid plus 8 H plus. 4 electrons are going to cancel with my 4 electrons here. The only other thing I have as a reactant is N2H5. Products, again, 2 manganese ions, 4 waters, and then we're going to have N2 gas plus 5 protons. All right, the only thing that's common here is protons, 8 and 5. So these 5 will go away and leave me with 3 here. I forgot in my A to C combo to figure out my E cell. So E cell equals my reduction plus my oxidation. So in this case, we're going to have my reduction is positive 1.23 plus negative 0.96. Right? And I did not figure this one out. So 123 minus 0.96 is 0.27. Still positive, so it's spontaneous. E cell for my last one. So my reduction is going to be positive 1.23. Oxidation is going to be positive 0.23. Okay? And so that will equal positive 1.46 volts. So again, just some very detailed, not overly difficult, but you've got to make sure you keep track of all your species, all your numbers, all your coefficients to make sure that you end up with the right overall equation and the right overall value for E cell.